All right, everyone. I want to welcome everybody to the CUNY Technologies webinar on Steam Basics. My name is Rick Kobolinski. I'm the product manager of CUNY Technologies, and I want to give you a little bit of my background first. As you could probably tell from my profile picture on the slide, I've been around a while. I started as a steam fitter apprentice way back in 1971, and for 41 years I worked in the Philadelphia area, HVAC and steam systems. And I even spent about a year and a half working at the Limerick Nuclear Power Plant in Pennsylvania back in the early 80s. I worked at area refineries, a boatload of universities, a lot of office high-rises, U.S. Steel in Morrisville, Pennsylvania, and countless industrial and commercial facilities. The last 20 and a half years of working in the field, I was the owner-operator of a mechanical contracting company. We were an in-house contractor at a major pharmaceutical company in the area. So I come at this subject about steam with a lot of field experience and a great deal of respect for the awesome power and capabilities of steam. Now, if you have any questions throughout the webinar, please enter them in the chat section that appears on your screen. And at the end of the presentation, we'll be answering your questions as long as time permits. If we don't get to your question today, we will follow up via email later in the week. All right, today we're going to go over the steam basics and how they apply to heat transfer. And we'll look at flash steam and different types of steam traps. Also, proper steam system piping, which is critically important to the overall system efficiency. I don't know if you're a design engineer or an installation contractor or a facility manager, you'd be responsible for the proper function of your steam system. It's very important for you to have all the information you need to make proper decisions. We'll finish up with a Q&A segment, and let's get started with respect. Aretha got it right, respect. She knew that steam should be treated with the utmost respect for its awesome energy capabilities, but also for its potential dangers. Aretha knew steam. All right, for the basic definition of steam, starting at the very basic level, you should know that steam is created when water is heated to its boiling temperature until enough heat energy is absorbed to transform the water into a gas. The heated water molecules begin to agitate, then separate, and they expand their volume dramatically. In fact, when water flashes to steam, its volume increases by 1,600 times greater than the volume as water. Conversely, as steam condenses, the volume decreases by 1/1600th. And just remember, as the steam pressure builds inside a pressure vessel or piping, the steam temperature increases correspondingly. And now we look at why do we use steam? Now, steam is used in a multitude of places, but if we're in the mechanical trades, construction, we focus on three specific areas. We use steam because it contains enormous potential energy. We could take advantage of very high velocity steam to drive turbines, to generate electricity in all the nuclear power plants, and also all the fossil fuel plants. They all use steam to generate all their electricity. Steam is used most importantly to us as a heat source for heat transfer. And this is where it holds a special place in my heart. It can be used inside steam preheat coils in an HVAC world because it can heat the incoming frigid outside air, and used in various types of heat exchangers also. All these heat exchangers can generate domestic potable hot water or heating hot water or a variety of other hot process fluids or slurries. Steam tracing is another example where steam is used for heat transfer. Steam is run through copper tubing that's strapped to a pipe that contains a fluid that may be susceptible to freezing. Steam is run through the copper tracing line, continuously transfers the latent heat energy to keep the pipe's contents from freezing or solidifying, as in the case of number 6 fuel oil lines. Steam can also be used in humidifiers inside air handling units to add moisture where needed in a form of a atomizing mist inside the HVAC airflow, and that'll increase the humidity to the proper levels. All right, we're going to get into some of the basic steam terminology to help us as we move forward. The very basic is the BTU. The BTU, British Thermal Unit, is the basic unit of measurement for heat energy. The strict definition is that 1 BTU is the heat energy required to raise 1 pound of water at atmospheric pressure, 1 degree Fahrenheit. Now, saturated steam is a little tricky for newcomers to steam. Saturated steam is dry steam that is saturated with heat energy. It is not water moisture saturation. You also may hear the term wet steam sometimes. And wet steam is just a mixture of steam and water. It's not considered suitable for proper efficiency of heat transfer. You'll use wet steam sometimes in a steam gun to clean the pavement or clean some equipment covered with oil or dirt. Remember, for every temperature of saturated steam, there's a corresponding pressure. We'll see that when we get to the steam chart. Latent heat. It's the heat energy required to change the boiling water to steam. It's the heat energy that really makes steam steam. This is the heat energy that we use for the best heat transfer. And we also have sensible heat, and technically, sensible heat is considered the heat content shown in BTUs in water between the freezing and boiling points. It's also known as heat of the liquid, but in our circumstances, we typically think of it as the heat energy in the condensate after the steam condenses back to its water state. And then we have condensate. That's the water created by the loss of heat in a steam system or a process. In other words, as steam gives off all of its latent heat energy, it returns to its water state. We have to be able to understand these basic steam concepts to help us design, install, and properly maintain a functioning steam system. Now we're going to go to a simple steam system diagram, very basic. We use this simple diagram to really help us understand the steam loop cycle and the concepts that go into a good, efficient steam design. We'll start at the lower left with the boiler, where heat's supplied to the water chamber, steam is generated and travels out through the steam system. Next, we'll look at the steam main up at the top of the diagram. It should be properly sized to accommodate the heat energy needed for the building's requirements. Next, you'll see the 2 drip legs off the bottom of the steam main. Their function is to allow condensate that forms inside the steam main to gravity flow down inside the drip leg and out through the drip leg traps that are shown there. You do not want excess condensate laying on the bottom of your steam main, because the velocity of the steam traveling through the main can pick it up and send it down the length of the main at speeds of 100 miles an hour or more. This is called water hammer, and it's very, very dangerous. Steam system damage can occur as a result of a catastrophic system failure due to water hammer. And it could also cause painful scalding personally and severe bodily harm or even death. I have personally been in mechanical rooms where steam water hammer, oh boy, makes you think that valves or equipment are about to blow apart. And believe me, that can make you want to change your diaper. Next on the diagram, we'll look at the process steam equipment. These are the pieces of equipment that use the steam for its heat transfer capabilities. And the kettle that we show here has steam flowing around the outer shell jacket of the vessel, and that heats the liquid contents inside the kettle. If this was a cafeteria kitchen, they're probably making chicken noodle soup. I could see the chicken in there now. I could really smell it now too. I'm getting hungry. When's lunch? The other piece of equipment shown is a steam coil, where the steam is fed into the copper coil tubes, which provide the heat energy to heat up the HVAC air passing through the fin pack of the coil. Usually, steam coils are used for preheating outside air in cold conditions. And once the steam gives off its latent heat in those pieces of processed steam equipment, its condensate will flow downward to the processed drip traps, and from there to the condensate main. The processed steam heating can produce much more condensate than a steam main drip trap. So care has to be taken to select the properly sized steam trap based on the heat load of the equipment as specified by its manufacturer. Now we see the condensate return line. It shows a severe pitch to allow the condensate to gravity flow downhill to a vented receiver. And you see the condensate running downhill. Take pains to properly size the condensate return line to allow the proper gravity flow and not have any back pressure, which could cause backups in your system. That would result in poor heat transfer in your equipment. We don't need that. Next, we're going to see the gravity condensate return flow into the vented receiver at the bottom right. From there, the condensate return pump, which in this case is a steam motive pump, uses steam pressure to push the condensate back towards the boiler. And you may elect to use a vented condensate receiver, electric pump, simplex, duplex pump. Uses electrical pumps to push the condensate back to the boiler room. As condensate flows back into the boiler room, it enters the boiler feed tank, collects the water. From there, a boiler feed pump forces the proper amount of water back into the boiler for generation back into saturated steam, which completes the steam loop cycle. All right, here's some typical reasons for poor system performance. If you're a hands-on person or a design engineer, you have to be aware of that to make sure you specify the proper techniques and do all the proper work to make sure you have good system performance. The first item that would cause a poor system performance is excessive water in the form of condensate in the system. It could lead to really poor heat transfer and could possibly cause some dangerous water hammer. This is caused by different things, usually undersized piping on a steam main or a condensate main or an undersized drip leg diameter that can cause that pesky water hammer. It could be a blockage in pipe strainers before your traps don't permit the condensate to flow through easily. And because of excessive back pressure in a condensate piping, that doesn't allow the proper flow of condensate. Check the size and look for possible back pressures inside the receiver vent line. And come to think of it, speaking of problems, one problem I just encountered recently was a poorly insulated steam main that fed a bank of steam preheat coils in the basement of a Philadelphia school building. In fact, there was no insulation on this 3-inch steam main. The steam main ran exposed to about 20 feet of an outside air plenum in the ceiling on a 15-degree day before dropping down into the bank of the vertical steam coils. Just think of that big squirrel cage fan inside the air handler drawing in 30,000 CFMs of 15-degree outside air, and just wicking away that heat energy from the exposed steam line before it ever reached the intended preheat coils. 3 of those coils were split from frozen condensate, and I was there to measure up the replacement steam coils. Okay, next item is causes poor system performance can be air. Air is really an unwanted byproduct of steam generation, because when the system is shut down, vacuum is created that can draw in external air through leaks and other openings in the system, vacuum breakers and the like. Air in the system can really reduce the heat transfer, reduce the temperature, since air acts as an insulator. And air inside the steam system can really promote rapid corrosion. Corrosion, along with dirt, scale, and debris, can lessen the heat transfer inside heat exchangers or coil tubing, and can wreak havoc with causing control valves to be blocked. Hands-on guys have probably seen that, clogged up control valves. Poor piping practices are usually the most infuriating for me because of that could cause poor system performance, mainly because with basic knowledge and a little bit of effort, these issues could have been avoided in the first place. You have to pay attention to pitch. You have to use gravity when you can. Because remember, gravity is your friend. Use the proper hangers at the proper spacing. You don't want to have improper spacing and have a return line sag and have low points for condensate, or even worse, sagging in steam mains that can puddle condensate and cause water hammer. You have to use the proper steam traps for your specific applications. Use the proper pipe and the proper fittings. And for contractors, don't use that 150-pound malleable 90 because you ran out of cast iron 90s. Use the carbon steel Schedule 80 pipe that would give you a longer resistance for failure due to corrosion. If you use shortcuts, they're going to catch up to you. I can promise you that. Try your best to do it right the first way, the first time. Let's talk for a minute about steam expansion. The latent heat of steam can cause considerable expansion of the piping system, especially at startup, when you're starting up from an ambient temperature. You must account for expansion, especially on long straight runs of pipe. Steam expansion joints are manufactured, specifically manufactured expansion joints that account for steam expansion. Or you could do it like the old timers like me used to do it. Install simple expansion loops in the middle of a long piping run and utilize cold spring and a proper anchoring, and you're good to go. For the young pups watching today, you may want to Google that. And that leads us on to flash steam. Okay, flash steam can be good or bad in a steam system. Results from very high temperature condensate moving suddenly from a higher pressure to a lower pressure. The heat energy in that high temperature condensate under pressure flashes back to steam when it enters an area of lower atmospheric pressure. Some facilities have utilized flash steam by reclaiming its latent heat energy, so they could get basically free steam that they use in an economizer heat exchanger to possibly preheat incoming domestic cold water before it enters the domestic hot water heater, and thereby they save some energy. Saving energy is a good thing. The cons of flash steam are the potential water hammer and overpressurizing drainage problems for the condensate. That leads us on to the steam traps. Basically, the best way to get rid of condensated air in a steam system is by use of steam traps. And a steam trap is an automatic control valve that removes the condensate and the air from a steam loop system, prevents the loss of live steam in doing that. First, we look at two types of mechanical traps. We have the F&T trap, or the floating thermostatic, that has an internal mechanical hinge float device you can see in the cutaway here. And when collected trapped condensate raises the float ball, which in turn opens the discharge port, the steam system pressure forces the condensate out through the discharge port. When the condensate level drops, the ball flow drops, the discharge port closes, not allowing any loss of live steam. It's pure genius. Wish I invented that. The F&T trap also has an internal thermostatic air vent near the top of the body inside that allows air evacuation from the steam system through the trap. And F&T traps are usually recommended for use on steam main drip legs, condensate removal and heat exchangers and process equipment, and also steam tracing applications. They could handle a wide range of steam pressures and are considered quite good at removing air from a steam system. F&T traps have rebuild kits available for replacement of the wore out internal parts, and they're fairly easy to change them out. Hands-on guys have probably had a lot of experience of changing out steam trap guts. Next, we're going to go to the inverted bucket trap. And this trap uses a internal bucket, inverted bucket design, and it collects condensate which floats the bucket up to a specific elevation inside the trap body, and that opens up the discharge port. Again, live steam pushes the condensate out, and the port is closed again as the bucket drops. This, like in the FMT, does not allow live steam to escape into your condensate system. It has a simple and a rugged design. It looks pretty rugged, and you usually have a longer service life than an FMT trap, but is not the best selection for air removal from steam systems in critical systems. And it's really not recommended for use in freezing conditions. Next, we get on to the thermostatic trap. This trap has a bimetallic element that controls the condensate discharge by sensing and reacting to the temperature difference between a steam and a cooler condensate. It's really extremely rugged, can handle very high pressures and temperatures. It's very versatile. They're suitable in drip leg applications, as well as small to medium-sized batch process systems. Since they can be installed vertically, they're a good choice for steam tracing applications and freezing conditions. And we go on to thermodynamic traps. It's a simple and compact steam trap. It only has one moving part. It's a simple disc that opens to allow condensate discharge, but closes in the presence of steam. And a single model can operate in a wide range of pressures. Has very rugged design, suitable for steam tracing applications when you install it vertically. And it's suitable for higher pressure drip leg applications. And it does have a limited ability, though, to vent air from a steam system. Then the next trap. Now we have this trap that will take the steam out of any mouse. It's a simple classic design and very economical. So what we want to take away from all this, there is no perfect trap. You have to know your application, know your existing conditions. All right, now let's get into the tools we could utilize. Here you're going to see some of the charts we use in making trap selections. The chart on the left shows you how many pounds per hour of condensate you must account at a certain pressure in a certain pipe size per 100 feet of steam main. The top chart shows you warm-up loads. That's the amount of condensate generated when you're starting up your steam system from atmospheric pressure at ambient temperatures until you reach your full system pressure. You're going to be condensing a lot more of that latent heat energy inside there on startup. The bottom chart shows the running loads, and that's the pounds per hour of the condensate that you generate once your steam system has been running at full design pressure and really fully warmed up. I don't know about you, but I really love the smell of a steam main at startup. I really can't explain it. The hands-on guys out there know what I'm talking about. Maybe some of the commissioning engineers out there have experienced it also. You got to heat it up low and slow, and then you start to smell that unmistakable smell. Oh, steam, nothing like it. Respect. All right, back to the program. The chart on the right is the famous steam table. It's the touchstone of all things steam. It will show you the temperature of steam at certain pressures, as well as the amount of latent and sensible heat. It show you the volumes of steam and condensate, and it's steam's version of the 10 Commandments, basically. We're going to look at another chart on more tools you could use. This is a very important chart, the steam properties and flow characteristics chart. And the chart shown here, it's invaluable for selecting steam line sizes once you base it on the proper velocity parameters. Don't forget that steam flow is rated at pounds per hour of condensate. This chart looks intimidating if you're not familiar with it, but you spend some time with it, you get to know it. It could be your biggest friend in doing your own calculations. It's a great tool. Don't be afraid to use it. Now we're going to look at some applications on steam line drip examples. What we want to do is we're going to look at the first highlighted example. Shows a properly sized, configured drip trap assembly. Note that the recommended 6-inch long dirt leg below the level of the steam takeoff, the level of the steam trap takeoff. Now, that's the industry standard for all drip leg assemblies. An operational blowdown valve at the bottom of the dirt leg really completes the standard design. Listen carefully because the next rule is very important. Here's how you properly size the diameter of a drip leg. I've seen a lot of wrong size drip legs and can cause some real problems with water hammer and real serious problems in steam systems. For steam mains up to 4 inches in diameter, your dirt leg diameter should be the same size as your steam main. How many of us have seen a 8-inch main with a 2-inch drip? For steam mains over 4 inches, your drip leg pipe diameter must be at least half the steam main diameter, but never less than 4 inches in diameter. That means a 6-inch steam main should have a 4-inch diameter drip leg, not a 3-inch diameter drip leg. And for long piping runs, you try to err on the side of caution and install drip legs every 150 feet or so on the run. This will keep your water hammer to a minimum and it'll help eliminate the premature system failures. Now, the middle highlighted example shows the proper method of installing a steam takeoff from the steam main. Ideally, it should come off the top of the steam main to ensure getting dry, saturated steam for your steam equipment. Takeoffs taken from the bottom of the steam main are more likely to contain condensate with your steam, won't give you the best available dry, saturated steam. You'll be starting out behind the 8 ball already. The steam trap takeoff is properly installed in this. The drip leg is the same diameter of the takeoff, which is good. Note that the PRV takeoff is located above the steam drip trap to ensure delivery of dry, saturated steam. Just remember that every steam control valve must have a drip leg with a trap located directly preceding it. This will not allow condensate to build up against a closed control valve, because if that control valve opens with a leg of hot condensate behind it, there will be one big water hammer, and that could do a lot of expensive and dangerous damage to downstream steam systems. Now we're going on to the last line, steam line drip example. It's usually recommended with changes in steam main direction, and especially with a change of steam main elevations. A drip leg with a drip trap is required. And in this example, you see a full main size drip leg. You'll see the 6-inch dirt leg, see the blowdown valve, and the proper location of the drip leg trap takeoff. In this example, this could eliminate the possibility of water hammer with a change in elevation. Remember, the water hammer is one of the prime reasons for the premature failure of a steam system. All right. Now, for a properly functioning steam system and system piping, there's a few things you have to keep in mind. Just got to remember that water, condensate, always runs downhill. I just love that. Then you have to use your brain. Always use common sense when working with steam. It can be dangerous. It can be awesome. You just have to treat it with respect, just like Aretha does. We touched on some of the basics of steam here, and hopefully you could apply some of the principles you've seen today in your particular situation. All right, we're going to go over a couple of capabilities of CUNY technologies. We get into a lot of coils, heat transfer equipment. We want to go over a couple things with you. First of all, we want to point out the shell and tube heat exchanger. That's now it's been the industry standard for quite a long time. Horizontal design, steam to hot water, heat transfer. You'll see the steam bundle with the tube sheet. Usually you have steam in the shell, water in the tubes. This is showing a 2-pass shell and tube heat exchanger. These are pretty common and they've been around forever. Next, we want to show you some steam coils. The coils we have up here are steam distributing coils. You can see that on the right-hand side. You can see the 1-inch steam distributing tubes on the left-hand manifold. On the coil on the left side, you can see our Cooney freeze block technology. Shows you the built-in vacuum breaker and our patented freeze block technology, which you could install this on your steam coils, and you could really eliminate problems with freeze damage with condensate building up and freezing inside your steam coil. Really does a good job, but we're going to be sending some handouts along after this webinar is over that's going to go over some of the possibilities that you could use in your system. All the local people near Philadelphia know us. We get out and about in the tri-state area here, but any of the national people that are interested in freeze block, you could take a look at our handouts and also give our office a call and we could bring you up to speed. Now we're going to show you some of the steam specialties. Right now, Cooney Technologies is a stocking distributor for Watson McDaniel. They're a local American-made product company not too far from us. We like all their steam traps and control valves, the receivers, the valves for PRV stations, for pressure reducing valves. They do a great job selecting, supplying all the steam specialties. The next we're going to look at, upper right side, we're going to look at it's a motive steam condensate pump. In the old days, you only had the mechanical electrical pumps that would have a float inside. Condensate level rises. If you have a duplex pump, you would have a lead lag controller inside. The float would kick on. If it can't keep up, the second pump would kick on. And a few years back, the motive force condensate steam pump was invented. It also has a float inside, and it's really powered by motive steam in the top of that unit. It takes motive steam pressure. When the condensate fills that, the float level rises, opens up a steam valve on top, and the steam system pressure pushes the condensate out of that steam past the downstream check valve to prevent any backflow, and it would send it, depending on your motive steam pressure, it would send that over to your boiler room. Next thing we want to look at is our pride and joy is the Cooney Thermopack on the left-hand side. It's a vertical steam heat exchanger. It utilizes the latest technology for the welded shell and coil steam to hot water heat exchangers. We have quite a few of them out there and more on the books with some local clients and Ivy League schools. And basically, you could take a look at it. We would manufacture the skid. We could customize it to make it fit inside your mechanical room if you have height requirements, if you have limited space. You can see the vertical design uses a very small footprint. And we utilize the shell and coil heat exchanger. You can see the cutaway version here. You'll see the top right connection. You have your steam coming in, goes through it's a dimpled, braided, welded stainless steel tubing that coils down to the bottom exchanger, and the bottom right connection has the condensate that exits the heat exchanger. On the bottom left side, you have the inlet for if you're using this for domestic water, you're going to have your cold water inlet here, and your hot water outlet is the top left. So as the cold water inlet comes in, it's basically a counterflow design. So we can oversize this to make this a subcooling unit. So as your cold water comes in, it's picking up the sensible heat from the condensate in the shell and coil tubing. Then it picks up the latent heat as it gets up higher in the heat exchanger and exits through the top left out to the system, whether you're running 120, 140 degree water. One of the recently supplied Ivy League heat exchangers that we delivered, we could give them 820 gallons per minute of 180 degree hot water, and subcool their condensate, so their condensate's coming out at 110 degrees. For local people who are Veolia customers or any kind of district energy customer, they're sending out your steam with about 180 pounds pressure. They bring it into your building. It's up to you to take that steam and convert it to your hot water system or your domestic hot water system. And district energy usually don't take any condensate back. You have to get rid of your condensate on site. So because, speaking for Philadelphia, it's a code requirement that you cannot dump any hot condensate down the drain at 140 degrees or more. So that's why these subcooled units are really important, where you could drop your hot condensate and subcool it down to, say, 110 degrees, 120 degrees. You could put your hand under it. You could just send it right down the drain. You don't have to put a 3/4 inch garden hose and leave it on 24/7, stick it in the drain to quench that hot condensate that's coming in. That's what a lot of customers do right now. They just think of all the water they're wasting. If you aren't on a district energy system, if you're returning your steam back to the boiler room to be regenerated, it's a good idea to just use the subcooling aspect to reclaim all the sensible heat from your steam. You're paying for it. You might as well get the BTU benefit out of it. And as your condensate comes out at a lower temperature, it's a lot easier once it reaches your vented receiver. If you have a simplex or a duplex electrical pump receiver, it's a lot easier in your pump seals. It's going to make that last a lot longer. And it's really a great design. So we're really proud of that. If anybody wants to see more about it, we could give you more information about it. And we're only too happy to talk to you about it, and we could customize it to fit your situation and your needs. And that's about it for our capabilities page. And do we have any questions? Caitlin, are you there?
I'm here. Can you hear me?
Yes.
All right. Thank you so much, Rick, for sharing all of your steam knowledge and experience with us today. It looks like we do have a decent amount of questions. I think we're kind of running out of time here, so we're going to try to hit as many as we can. And again, the rest we will get back to you guys via email, if not today, later in the week. And for anybody wondering, we will make the slides available to you as well as the recording of the webinar. So we'll pass that along to you. So it looks like we have a first question here. What does condensate lift mean? I've heard some tradesmen talking about it, but don't really understand the concept.
All right. First of all, I'd like to thank Caitlin for all her help. She's our marketing guru, and she's done one hell of a job getting this webinar together with me. Okay, condensate lift. In a steam system, when you're generating condensate, if you don't have the capability to gravity drain your condensate to your vented receiver and then pump it back either with motive steam pumps or a simplex or duplex electrical pump back to your boiler room, you may have to lift your condensate up to a point where you could gravity drain it back to the boiler. When they talk about lift, they're talking about basically the water column. If whatever steam pressure you have on your system, you can use that to lift your condensate up to a certain point. You remember that every foot of water or condensate in a vertical column, it takes about, it has about a 0.433 pounds of pressure for every foot of water column. So if you have a 15-pound steam line, you could use that to figure out how high you could pump your condensate or push your condensate with that steam pressure.
Okay,
just one other thing. Some people fall into the trap and thinking their steam line can, your steam pressure could push unlimited amounts. They dump it into their condensate main. They don't realize that the condensate main may have medium pressure or high pressure connections to it that somebody else connected in the previous project. And that could really flood that condensate system or cause back pressure. Won't allow your low pressure condensate to dump into that condensate receiver. Or if your vented receiver is undersized on its steam vent. I've seen a lot of places where the steam vent comes off a vented receiver and it travels up through the building up above the roof. And everybody who does a project says, oh, here's our steam main, let's tap into that. And they start tying in all over the place. You may not see it in the mechanical room, but in upper floors or in a penthouse mechanical room, they're tapping into that line, and that could cause back pressure. That could really, you don't have a true atmospheric vent at that point. You really have to pay attention to that.
All right, and then this question here goes actually back to the piping diagram, it looks like, and it asks, what is on top of the vented receiver riser? Shouldn't a vented receiver be wide open to the atmosphere?
Okay, now that goes hand in hand with what we just talked about.
Yeah.
We didn't really have enough time to go over every little facet of a steam system. And this particular diagram shows a device that's called an exhaust head. If you're venting to the atmosphere from a vented receiver, pretty good chance that you're going to have some flash steam that's generated when the condensate under high pressure reaches a atmospherically vented flash tank or a vented receiver, and that could be dumping a lot of flash steam up above the roof. And as soon as it hits the atmosphere, it starts condensing in the air, especially in colder temperatures. And that section of roof, it looks like its own rainforest. It'll be raining all the way around that vent line. And that could cause some serious damage to the roofing material, especially if you have a rubber roof, especially in the wintertime. The biggest use for this is people that have a rubber roof and a flash steam coming out of the open vent line. It'll rain down in frigid temperatures on that rubber roof, and it'll automatically freeze up right away, and it makes it a real hazard to walk across that roof. At the pharmaceutical, I put steam heads on top of every vent line because one of the main engineers was walking on the roof one day when the flash steam was coming out. Even though the outlet was about 6 feet above the roof line, he got doused pretty good with a rain cloud of water. And after that, yeah, we put on the flange and a exhaust head on that. Now, it restricts the open vent a little bit, but it really separates the entrained water from the flash steam that's being discharged up above that vent line. And it collects it in a little ring, and it usually has, I believe it's a 3/4 inch tap connection on the bottom, NPT connection. And you can run a piece of pipe down to the roof line and run a piece of pipe over to your roof drain, maybe increase it a little bit if you're worried about it freezing in cold conditions, but you would run it over to a roof drain just so that water is not freezing on a rubber roof surrounding that vent line. It's a really safety concern more than anything else, but it's critical to a good system design. You don't want to have any front dangers up on a roof.
All right, Rick, it looks like we're gonna be out of time for the rest of the questions. I'm gonna copy these down and email everybody the answers. It looks like we still have several left here. So just want to take this time to thank everybody who joined us today for the webinar. Hope you got something out of it today. It's our first webinar, especially in this new world that we're living in with social distancing. So thanks for hanging in there with us. We're just going to ask you guys at the end if you could take some time. There's a survey at the end to just rank us on how we did today, any feedback you have, and for future webinars, any topics you'd be interested in learning more about or discussing more. We'd really appreciate it.
All right, now I'd like to take the chance here to thank everybody for registering and attending. Or if you're taping this, you watch it later, I hope you get something out of it. I really want to thank Caitlin again because she was very instrumental in getting this webinar together. So everybody, thank you and stay safe.